Okay. Welcome everyone to Geometric Structures Lab at Fields and at CIMCRIA Barcelona. We're very happy to have Francis Bischoff from University of Regina visiting us at the Barcelona location. And he's going to give a talk which is related to a talk he gave a couple of months ago um, about the signature of paths, but today he's going to be talking about thin homotopy and the signature of piecewise linear surfaces.
Okay, thank you. Um, okay, wait, possible. Maybe I'll turn on the video so people can see me as well.
Just this. Is that good? All right.
Okay, great. Okay, so, oops. Okay, so here's the plan of the talk. I basically, it's broken up into two parts. One of them about paths, which I'm going to just briefly review this time, paths and the path signature. And then for most of the talk, I'll talk about services. And this is joint work with Derek Lee. Yeah, and I would say also contributions from Camilo Arias-Abad. Oops. Okay, so in a bit more detail, I want to, two of the things that I want to focus on is explaining thin homotopy for surfaces and also a construction of a two group of piecewise linear surfaces. Okay, and here's sort of a table of contents. So the talk has four parts: path, services. So paths will be review, services will be sort of an overview, and then I want to get into more details in the last two parts about thin homotopy and then piecewise linear paths and services. Okay, so starting with paths and connections. Okay, so the setting here is I'm going to have P nabla, a principal G bundle over a manifold that's equipped with a connection. So locally, a connection, you can write it as nabla is D minus alpha, with alpha a one form valued in the Lie algebra of the group G. Why does it do that? Okay, now if the connection is flat, then it determines a parallel transport homomorphism, which is a homomorphism from the fundamental groupoid of M to a groupoid of automorphisms of the principal bundle. If the connection is not flat, then there is still a parallel transport homomorphism, but it's from a sort of a bigger groupoid, which is a groupoid of, I'm calling it the thin fundamental groupoid, so it's paths up to what's called thin homotopy equivalence. Okay, so I think, yeah, so here's a reminder of the definition of thin homotopy. So I have two paths here, gamma and eta, and they're thin homotopic. If there's a smooth homotopy, H, between them, with the property that the rank of the differential of the homotopy is bounded by 1. So in other words, it cannot sweep out any area. So here's a typical picture. It looks sort of like a tree. So all that you're basically allowed to do is reparameterize your paths, and then you're allowed to either add retracings, a little kind of excursion where you go out and you come back, or you can cancel those, or you can add new ones. So see here, I've gone from this sort of blue path gamma to this green path eta. Okay, so essentially thin homotopy consists in reparameterizations and cancellation of retracings. There's another equivalent definition of thin homotopy for paths, which says that two paths are thin homotopic if and only if you can find a homotopy with the property that the image of the homotopy is contained in the image of the starting path and the ending path. So you can see this in this picture here, that this pink square gets sent to the union of the blue stuff and the green stuff. There's another interesting equivalent definition, which says that a loop is thinly null homotopic, so equivalent to the constant loop, if and only if the holonomy around this loop is trivial for every SL2R connection. And the group SL2R is not really important, it's just important that it's simple. Okay, so these results, I think you can find them in a paper of Tlass. Okay. Okay, so now I want to construct what I'm going to call a group of thin paths, and it's going to be associated to a vector space. So given a vector space V, we can take the thin fundamental groupoid. So paths modulo thin homotopy, and the groupoid structure is given by, the groupoid product is given by concatenation of paths. And because we're in a vector space, this groupoid is equipped with an action of V by translation. You can translate a path around. And so we can take the quotient of the fundamental groupoid by this action, and that gives us a group now. So this is what I'm calling the group of thin paths. So you can think of an element as a path where it's sort of, you're allowed to translate it around in your vector space. So if you have two paths and you want to multiply them together, you just need to kind of translate them so that their endpoints meet, and then you can concatenate. So this group, now it has a natural homomorphism to the vector space, which is given by displacement. So it's a homomorphism to V, where we think of V as an additive group. And you can think of this as saying that this group of thin paths has an action on the vector space V, and you can consider an action groupoid for that, and that recovers the thin fundamental groupoid. So these are sort of two dual pictures of thinking about it. Okay, any questions about this? So this is the first important object, this group of thin paths. Okay, so now I'm going to recall a second fundamental thing that you can construct using a vector space, which is the Freely algebra. So I'm calling it LV. It's the Freely algebra generated by V. And I'm denoting by K0V its formal integration. So in more detail, if we take the tensor algebra generated by V, which you can think of as an algebra of non-commuting polynomials, then LV, well, the tensor algebra, it's an algebra. So in particular, it's a Lie algebra using the commutator bracket. And sitting inside of there, you have the generators V. So LV is what you get when you just take the subalgebra that's generated by V. So you take, say, these basis elements Z1 up to Zn, and you just start taking brackets as much as you want, and that fills out a subalgebra, which is LV. Okay, and we can also view this group K0V in terms of this tensor algebra by just formally taking exponentials of elements in LV. Okay. Okay, so
Sorry, Francis, can I ask? So at this point, what do I think of when you say formally take exponential? Like, do I think it takes values in formal power series?
exactly.
Okay,
Non-commutative power series.
thank you.
Okay, so now the way to link a Freely algebra and in this group of paths is through parallel transport of a connection. And there's a sort of a tautological connection that exists on any vector space, which I'm calling it the tautological connection. And it's a connection on a vector space V valued in the Freely algebra on V. And it's essentially given by D minus the identity of V, where I'm thinking of the identity of V as living inside V dual tensor V, where V dual, I'm thinking of them as constant one forms on V. And then the second copy of V, I'm thinking of them as generators of the Freely algebra. So if you identify V with Rn, you take a basis Z1 up to Zn, and then you let x1 up to xn be the corresponding dual basis, which are coordinates on Rn, then you get this expression here for this tautological connection. And this is a non-flat connection. It has curvature given by this expression here. Okay, and now you can take the parallel transport of this connection, and that gives you a functor from this thin fundamental groupoid to this group of non-commutative power series, K0V. One thing to notice if you look at this expression here is that this connection is translation invariant. So that means that if you have a path and you translate it, it won't change the holonomy. So that means that this parallel transport homomorphism actually factors through this as a homomorphism from this group tau1 of V to K0V. And given a path, its signature is exactly the non-commutative power series obtained by taking this parallel transport. So this is some sort of a transform that takes paths and converts them into non-commutative power series. Okay, so I'll tell you, so it's going to have components sort of in V, and then V tensor V, and then V tensor V tensor V, and so on. All the tensor powers of V. So I'm going to tell you the first two components, what you get. So you're going to get a component in V, which is in degree 1. And that's just going to give you the displacement of the path, gamma 1 minus gamma 0. So here I drew a path in blue, gamma. And by just looking at the endpoints, you get this vector in V. That's the displacement. Okay, in degree 2, the degree 2 part of the signature is in V tensor V, but this breaks up into something that's symmetric and something that's anti-symmetric. The symmetric part is determined by the displacement. So I've given this formula here. The ij component, the symmetric part of the ij component is just the product of the displacement in the I direction and the j direction. Okay, the anti-symmetric component is more interesting. So I've written it here. Here's an expression for the anti-symmetric component. And the way that you can interpret it is it's the signed area between the curve and the straight line connecting the endpoints. So sort of this area here between the blue and the diagonal line, and then minus this little area here. That gives you the component in wedge 2 of V. Okay, and then the fundamental theorem about this map, which was proved by Chen for piecewise regular paths, and then for much more general paths by Hamblian lines, is that this signature map is injective. So if you know the signature of a path, it completely determines the path up to translation and these thin homotopies. So reparametrization and sort of retracings. Yeah, and in fact, you could ask if you have an element of the tensor algebra, can you recover the path? I think this is an interesting question that has only been worked out kind of in the last few years, actually. It's how to go backwards. Okay, so that's the end of part 1 about paths, which is supposed to be a review of the last talk. So are there any questions about this?
But by how to go backwards, do you mean whether the map is surjective or producing some explicit inverse?
It's known not to be surjective. And I think the image is not well understood, but if you know that you have a non-commutative power series, which is the signature of a path, you know that, then how do you recover that path? That's the question.
I see.
Okay, so now I'll move on to surfaces. Okay, so for surfaces, here's the idea. So we want to define signature of surfaces now in Rn in order to sort of capture algebraically a surface. And in order to do that, we have to categorify all the concepts that came up when studying paths. So this thin group, as well as the group of non-commutative power series, they both need to be promoted or categorified to two groups. Connections need to be categorified to two connections. And the parallel transport needs to be categorified to a two-functor, or a homomorphism between two groups. Okay, so this is what I'll review now. So the first, well, what's the model of two-dimensional groups that I'm going to use? I'm going to use what's called a crossed module. So these were introduced actually in the 50s by Whitehead, and it's, I think, a very simple definition of compared to other definitions of two groups, at least. So a crossed module, it has basically four pieces of data, H1, H0, delta, and this little triangle. So I'm going to go through each of them in turn. So H0 is a group, and the picture that you should have in mind is as a sort of a group of paths. It might not literally be paths, but you should think of it in this way. It's a sort of a one-dimensional object. So you could see, yeah, so you have paths, which you imagine that you can concatenate. Then H1 is a group of surfaces, and I want to think of them as surfaces in the following way. So they're maps from a square into my codomain, with the property that three of the sides get sent to a point, right? So only one of the sides is allowed to be non-trivial. So I've illustrated this in this picture that the boundary of this disk, or of this surface, is just coming from this top edge of the square, and then all the rest gets collapsed to a base point x0. And the reason that you want to do this is that surfaces like this can form a group because you can concatenate them horizontally. You can stack two of these horizontally because on the horizontal edges on the two sides are just constant, and so two of those will always agree. Two of these surfaces. So you imagine that you have a horizontal concatenation, and this gives you a group H1. Okay, and then the third structure is that you have a homomorphism of groups from H1 to H0. And the way that you should imagine this is that if I have a surface sigma like this, I can extract the top path, the path of the top edge of the square. And this is a homomorphism because the group structure in both cases is horizontal concatenation. So if I horizontally concatenate two squares, then the top edge is formed by the horizontal concatenation of the two individual top edges. Okay, and then the fourth thing is an action of the group H0 on the group H1 by group automorphisms. And here's the way that you should think about it. So I have a square here in green, and I have a path in blue, and I want to act by the path on this square. So what I'm going to do is I'm going to take this path and I'm going to view it as a very thin surface. It's a surface, it's a map out of a square where vertically it's constant, it's only moving horizontally. And then I take two copies, I take sort of a forward copy and a backwards copy, and I stick them on either sides of my square. Okay? Okay, so these are all of the structures, and then they need to satisfy some axioms. The first one, it says that this homomorphism is H0 equivariant, where H0 acts on H1 in the way that I just described, and it acts on itself by conjugation. And if you look here, it's sort of clear that this action is going to satisfy this. Because if I look at the top edge here, it's going to be gamma, eta, gamma inverse. Okay, so if I just have this structure with just this condition satisfied, I have what's called a pre-crossed module. In order to get a crossed module, you have to introduce one more condition, which is a little bit more mysterious. It's called the Pfeiffer identity. So this is an equation that holds for elements of H1. So I have two surfaces, E and F, and there's two things I can do. On the one hand, I can take my surface E, take its boundary path, and then act on F with it. Or I can conjugate F by the surface E, and the Pfeiffer identity says that they should be the same. So this identity is very closely related to the interchange law in two categories. It's essentially the way that the interchange law is manifested in cross modules. Okay, any questions about the definition of a cross module?
Very naively, sorry, cross module, but those are groups, so one imagines that those are representations of something, if one thinks of modules, so is that the case? Or conversely, is there an actual definition of a representation of such a thing? Like, what is a module for a cross module? I don't know. Do they act somewhere? Very naive and random question, sorry.
Because of the word module.
Yeah, or otherwise, what is representation of it? Because I imagine one has an analogous notion for the algebras, right?
Yeah, so you can define, like for example, if you have a two-term chain complex, you can form a cross module of automorphisms of that, and you could consider homomorphisms of cross modules into that thing. That could give you a module over a cross module.
But that's not at all relevant.
I mean, the reason that it's called a module is because of the fact that H0 acts on H1.
Yeah,
That's the reason.
Yeah, and it's you should think, like he was explaining, it's like the fundamental group acting on the higher fundamental groups.
yeah.
Pi 1 acting on Pi 2 is a module. So that's the
I see. Okay.
Exactly. So they were introduced by White.
And that's why it's lost, okay. So there's something in the other direction there. Okay.
So they were introduced by Whitehead in the 50s, and what he proved is that these things represent all homotopy 2 types. Okay, so I'm going to give an example, the first example of a cross module, which is going to extend this thin group of paths. So this is the cross module of surfaces in a vector space V. So its construction is essentially due to Martins and Picken. Okay, so you have two groups, tau 1 and tau 2, a homomorphism and an action. And in fact, the pictures that I was giving before secretly were exactly describing this particular example. So the group tau 1 is the group of paths modulo translation and thin homotopy that I described before. The group of surfaces tau 2 is exactly a group of smooth surfaces, so maps from a square into V, which have these boundary conditions that 3 of the sides get sent to the base point, taken modulo translation and thin homotopy. So I'll return to thin homotopy in the next section. So for now, I'm not going to define it, but it's a natural equivalence relation on surfaces. And then the group structure is given by horizontal concatenation, and the map delta is given by restricting to the top boundary. And yeah, essentially, yeah.
I'm a bit confused about this action here then with this definition, because it looks like when you take this path gamma and you want to view it as a square, then 2 of the sides are not constant, right? The top and the bottom.
Yes, that's a very good point. But the point, yeah. So it looks like it doesn't work, but the point is that this path on the bottom. So on the path on the bottom is gamma constant, gamma inverse. So this bottom path is null homotopic. It's thinly null homotopic. So you should add on an extra square to kill that off.
Okay.
Like you should add on this you should imagine that maybe you add on the bottom a homotopy that takes gamma inverse to the constant.
Okay, that makes sense. Thanks.
Okay. Now two-dimensional gauge theory. So so now I'm considering a cross module of Lie groups. The two groups are H and G now. So you can, of course, differentiate this, and you get what's called a cross module of Lie algebras, which is essentially the same thing, right? Two Lie algebras, homomorphism of Lie algebras, delta from H to G, and then G acts on H by derivations, and delta is equivariant, and then an analog of the Pfeiffer identity holds. Okay, so this cross modules of Lie algebras is the correct coefficients for two connections. So here's what a two connection is. A two connection, at least on a vector space V, valued in this cross module of Lie algebras, it consists in the data of one, a G-valued one form A, so just a usual connection. But then you also have an extra thing, which is an H-valued two form B. And these should satisfy a compatibility that if you take the curvature of A, which is a two form valued in G, it's equal to delta applied to B. So A is not flat, but it's sort of flat up to this differential. Okay. Okay, so these give you the correct notion of two connections, and then you can take their parallel transport along paths and surfaces. Okay, so this is a theorem that's due to many people, in particular Schreiber, Waldorf, Martins, and Piggin. So I'm giving you a translation invariant version, but there's a more general version. But if you have a translation invariant two connection, then this induces a parallel transport homomorphism between cross modules from this cross module tau V of surfaces up to thin homotopy that I just introduced to this general cross module of Lie groups. And in particular, it associates an element of this group H to every surface X in V.
Sorry, could you tell me again what is the definition of a two connection on the previous slide, I guess? So it's just a cross module of this form.
It's a cross module and then a one form A valued in G and a two form B valued in H, such that B sort of lifts the curvature of A, or it sort of trivializes the curvature of A.
Right.
Yeah, this condition is important because what you want is that if I take a surface and I take its holonomy, which is in H, and then I apply delta to get something in G, that should be equal to the holonomy of the connection around this boundary, around the boundary of my surface. So you need to link together the surface holonomy with the path holonomy, and that's exactly what this condition here is giving you. It's sort of a non-abelian version of the Stokes theorem. Okay, so now I want to define a free cross module generated by a vector space, which is going to generalize the free Lie algebra. Okay, so
just as a question before you get to, what's your favorite example of a kind of non-trivial finite rank two connection? Have you ever thought of, in the same way that we study simple examples of connections on vector bundles, like the Hopf migration, let's say?
Oh, you mean like a particular space with a particular connection?
Yeah. Where you have some interesting choices for G and H, let's say.
I don't know specific examples, but you have like gerbs with connections. So you could take G to be trivial and then H to be an abelian group. And then you would just have a two form B. And then the surface holonomy would be sort of the integral of B over a surface.
That would be the usual U1 gerb.
Yeah, exactly. Yeah, if H was U1.
Francis, if I can ask also one question before moving on. I'm assuming that this crossed module description of a two connection is like a more explicit description. So if it's true that given a two groupoid, I can present it as this kind of cross module, and then that's the group theoretic data, and then this two connection is you're presenting it in terms of this cross module. But is there an analogous description in terms of like a representation of a two-Lie algebroid or something? And this is a more explicit description of what a two connection in that sense means, or this cross module description is the only description we have available for a two connection. Does that question make sense?
Yes. I think you can associate a sort of a two Lie algebroid or a cross module of Lie algebroids to any manifold and then represent connections as morphisms from that thing. Yeah, I
Okay,
think that
thank you.
that's available.
For example, the theory of superconnections is like that. If you take a graded vector bundle and you have a super connection in it.
That's true. A superconnection does not use a two cross module of Lie algebras, though. It just uses the tangent bundle. Another thing I should mention is that the underlying bundle, well, because I'm on a vector space, the underlying bundle is trivial. But you could have a higher bundle. Like the bundle itself could be twisted up. That's like what you get with a gerb. And this is not entering the story at all, because it's on a vector space. But that's somehow an orthogonal direction in a sense. That's about the topology in a sense, but this is more about the geometry of surfaces.
And just to clarify one thing, you're not here talking about the generalization of a flat connection.
No, a flat connection. So you can define a curvature of a two connection, and that's going to be a three form valued in H. And that could be flat, and that gives you a flat two connection, but the connections that I'm interested in are not flat. Yeah, because essentially on a vector space, we make everything trivial.
So in order for such a two connection to have a curvature, you would need to provide more data?
No, you just take basically the it's like you take the covariant derivative of B along A, because H is a G representation. So you can sort of differentiate B using the connection given by A. And that's the
And that would be a three form with values in H.
exactly.
And that would be the curvature.
Exactly. Okay. So so the free cross module of a vector space. So you have two Lie algebras, K0 and K1, you have a map delta, and then you have this action. So K0 is going to be the free Lie algebra generated by V that we considered before. Now this receives a map B from wedge 2 of V into this free Lie algebra by taking V wedge U and sending it to the Lie bracket of V and U. And from this map, you can generate a free cross module. So this is the free cross module of Lie algebras that's generated by this map B. So I won't tell you what it is in detail, but as a vector space, it's essentially a quotient of the tensor algebra of V tensored with wedge 2 of V. What's more interesting is the following theorem of Kapranov, is that you have an exact sequence. He computes the cohomology of this cross module. So in degree 0, you just get the vector space V. And but
Sorry, it was a bit fast. So K1V is the free cross module. You don't mean that. You don't mean that. It's just you're describing a cross module K0 and K1.
yeah,
The K1V is the free Lie algebra.
it's a sort of a so cross modules, it has sort of a Lie algebra in degree 0 and then a Lie algebra in degree 1. And the Lie algebra in degree 0 is sort of acting on the Lie algebra in degree 1. And it receives a map. So you can sort of forget to a category where the objects are just a Lie algebra in degree 0 and a vector space mapping to the Lie algebra. And the left adjoint of that is like a free construction.
I'm just trying to understand what K1 of V is.
Yeah, I'm telling you.
Okay, so what is K1 of V?
So it's the free cross module obtained from this map. It's a cross, you should think of it as like a cross module over K0V, and it's the one that's obtained from this map. Right, there's a forgetful functor from cross modules of Lie algebras to a category where you have a Lie algebra and a vector space with a linear map to the Lie algebra. And you just take the left adjoint of that. That's the free construction. So you're basically just going to let, you want K0V to act on this thing in as free a way as possible in such a way that it also gets a bracket. So if you start acting with the free Lie algebra on wedge 2 of V, you're basically going to generate the tensor algebra of V, tensor wedge 2 V. But then you have to impose like the Pfeiffer identity and so on, and that's going to give you a quotient of it.
So the quotient of TV tensor wedge 2V is obtained by imposing the Pfeiffer identity,
Exactly.
or is it also certain action identities?
In fact, you only need to impose Pfeiffer. Yeah. Yeah, in fact, it's sort of strange that the free pre-cross module is much more complicated than the free cross module.
So like it satisfies an easier to state universal property, but the concrete example which
No, it satisfies the same universal property, but the construction of the free cross module is much simpler.
satisfies the same property.
Well, I mean, it satisfies
Something different.
it satisfies a universal property within a category of either cross modules or pre-cross modules.
And that this physical structure gives you something much bigger. Yeah.
Exactly.
Okay, yeah, sure. Yeah. I mean, and it's big.
But is the map from K1 to K0 an embedding?
No,
So
no,
it's
no,
not
no,
it's not a sub-algebra.
no, no. So this is what Yapranov tells you. Is that the kernel of this map is this big vector space. It's the space of polynomial two current of. It's this. Oh, there's a typo. It's the space of closed polynomial two currents. Closed. So you have the co-Durham complex, and you have in particular this map from two currents to one currents, and you take the kernel of that. That's what this space is. And you should, the way that you should think of that is that I start with the free Lie algebra, it maps to V, and it has a big kernel. And I want to build a resolution of V. So then the kernel of this map is in a sense generated by wedge 2 of V. And so what I do is that I basically generate a cross module in a free way to basically kill off the kernel of this map. But now this thing has a kernel, and you could imagine continuing by adding more things, and you could get a resolution of V in this way. This is sort of the first step in constructing a resolution. Okay, and we can, again, just formally integrate this to get a cross module of groups, which I'm calling the cross module of formal surfaces. Okay. So now I want to relate this cross module of smooth surfaces to this cross module of formal surfaces. And in order to do that, I'm going to use a specific two connection, which is a tautological two connection. So it's supposed to be a two connection valued in this cross module of Lie algebras. So it's going to be a one form with values in the free Lie algebra of V, and then a two form valued in this K1 of V. And in both cases, so for this one form, I take the same thing as before, the identity of V, right? Where identity of V that's in V star tensor V. I view V star as something in omega 1 of V, and then V in the Freely algebra. And then for B, I take the identity on wedge 2 of V. So it's something in like wedge 2 V dual, which I think of as in omega 2 V, tensor wedge 2 V, and well, that's basically this wedge 2 of V is the thing that's generating this K1 of V. So in coordinates, you get this sort of explicit expression. Okay, so the surface signature is just simply the surface holonomy of this tautological connection. So it was first defined by Kapranov, and then these other authors studied it in some recent papers. And I guess Kapranov didn't call it the signature. The terminology signature comes from these people who work sort of in, well, like sort of stochastic analysis and stuff like that.
So this definition here, you're saying if you apply the theorem from before of Schreiber, Waldorf, Martins, Picken to this two connection and get the parallel transport, the corresponding higher parallel transport, then you get this.
Yeah, exactly. Exactly. And it's essentially, yeah, you can define it through iterated integrals or by solving some differential equations. So given a path, the component in the K0V is the path signature that I talked about in the first section. Given a surface, you get now a component in K1 of V, and this is the what's called the signature of the surface. In particular, I mean, if yeah, it's important to remember the kernel of this map is this closed currents. So if X is closed, then the signature, you can view it as a closed current, but I put the hat because you might have to take power series. So it takes any closed surface and it associates a formal current, something that you can pair with polynomial two forms.
Something you can pair with what?
With polynomial two forms. Right, because it's like a power series. It's like a you take the dual of the space of polynomial two forms. That's what this thing is. So you can pair with a polynomial two form and get a number.
Maybe also can you say so, because capital K0 was thinking, kind of saying like, yeah, essentially you just use Baker Campbell Alsdorf to express everything in this formal group by just saying it's generated by X of symbols in the algebra, and then you just apply formally with no correction Baker Campbell. But for K1, can you give another such intuitive, I don't know.
Yes, I'll explain at the end.
Okay, yeah, sure.
Yeah, but one thing is for sure is that within K1 of V, you have this as a subgroup.
Mm-hmm.
And for a closed surface, the signature is just something in here.
Mm-hmm.
And this is, so this is something that we checked with Lee, but it was sort of suggested by Kapranov, is that this is just the sort of the formal density that you get by integrating all polynomial two forms over the surface. Right, what is something in here? It's something that if I take any polynomial two form, it gives me a number. Well, a surface is something that if you take any polynomial two form, it gives you a number by integrating it. And that's just what it can't really be anything else.
But what is the closed superscript telling us about this density?
is that it evaluates to 0 on exact two forms or on closed two forms.
It evaluates to 0 on closed two forms.
Well, exact two forms. I mean, they're the same thing, but exact two forms. The integral of an exact form on a two-dimensional surface without boundary should be 0. That's what it's saying.
Sorry, just a confusion about the terminology. You're saying this is a definition of the surface signature, and then in the second line after this, you say given a surface, like the first component of this definition, you're also calling the surface signature.
Well, yeah, I'm saying that this map, which I'm calling the surface signature, but it really has a component for paths and a component for surfaces. That's all that I'm saying.
And did you have a previous definition of S1 of X?
No, 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 no. This is the definition.
I see.
Okay, that's the end of the section on surfaces. Any questions about this section? Okay, so I want to now talk about thin homotopy in some more detail. So here's the definition, which is that a thin homotopy between two surfaces, it's a homotopy, so it's a map from a cube into V, which interpolates between the two surfaces, but it has the property that it doesn't sweep out any volume in the sense that the rank of the differential is bounded by 2. So remember, in the case of, let me just go back to the case of paths. It was an analogous definition, but it was that it could not sweep out any area. So the rank was bounded by 1. And I just want to recall, thin homotopy of paths, it was reparameterizations and cancellation of retracings, and that was basically it. And also there was this property that two paths are thin homotopic if and only if you can find a homotopy whose image is contained in the union of the images of the two paths. Okay, so keep those in mind. Okay, so for thin homotopy of surfaces, you have the same thing. You have reparameterizations, those are thin, and cancellation now of folds. That's like the one-dimension up version of the cancellation of retracing. So something like this, if I have a surface and it has a fold like this, you can just remove the fold. Okay, but you also get something more non-local. So here's an example of a surface. So I'm taking a sphere. I'm going to project it to RP2 by identifying antipodal points, and then I'm going to map it into Rn, possibly with an embedding. And the claim is that this actually is thinly null homotopic, even though there might not be any folds to cancel. For example, if it could be an immersion or this map could be an immersion. So there will be no folds to cancel. Furthermore, there cannot be any null homotopy which stays completely within the image of the map. Because if it did, it would be a null homotopy for the map from S2 to RP2. And this is not possible because this map generates pi2. Okay, so in these two ways, thin homotopy for surfaces is much different than thin homotopy for paths. So thin homotopy for paths, what I explained in my last talk, is that it's very closely related to word reductions in free groups. You have a word in a group and you're just canceling out inverses to get to a minimal word. In particular, every word in a free group has a unique minimal representative. And the same thing is sort of going on with paths. If you have a path, you can sort of thinly reduce it to get a minimal path representing it. But this is completely not true for surfaces. Like if this map has no folds, then that means in a sense it's like a minimal word. There's no more folds to cancel. but it's not unique because I am saying it's also homotopic to a point. Thinly null homotopic to a point.
Francis, what exactly do you mean by surface here? Do you just mean like this map from a square? But what if I had like some Riemann surface or something like?
The map from a square. I mean, you
I
could.
mean, you're taking I times I, or like 0, 1 times 0, 1.
Exactly. Yeah, so I'm taking 0, 1 times 0, 1. I'm collapsing the boundary to a point because I want it to be a closed surface. So it's really a map from a sphere.
Sure. I guess, but like, what if I have something that can't just be realized as a quotient of like the square, like the unit square in R2? How should I think about like thin homotopy for like a genus 20 Riemann surface?
Well, you could either try to realize it as made up of maps out of squares that you sort of combine together.
Okay.
Or you could try to develop maps from higher genus Riemann surfaces and have homotopies being maps from the Riemann surface times an interval or something like that.
Where you still have this rank condition, I guess.
Yeah.
Or,
So that's
okay.
not what I'm doing because this is supposed to mimic usual homotopy, which is just maps from squares.
Right. Okay.
Okay. So the point is that because there's no null homotopy which stays completely within the image, in order to realize the thin null homotopy, we have to introduce new surfaces. And so that's the key feature of thin homotopy of surfaces, that you have to introduce new surfaces, and it can be sort of complicated how to realize this.
What do you mean you have to introduce new surfaces as domains, you mean?
No. As like I'm saying that the thin null homotopy cannot be contained within the image of the map. So if I have two paths that are thinly null homotopic, the homotopy lies within the union of the image of the starting path and the ending path. But this is not true for surfaces.
Yeah.
So you might have to introduce new surfaces that your homotopy might have to go into.
Oh, you mean you need to introduce a family of surfaces that retracts this thing to a point? A whole family of intermediate surfaces.
No. I'm saying RP2 is inside of Rn, and I might need to add on some more surfaces where my homotopy is going to move into those other surfaces.
Well, why do you say surfaces? It could be volumes.
No, because it's thin. It has to be thin.
Oh, I see.
Okay, so I'm going to give the homotopy for this because it's quite explicit and illustrative, I think.
Sorry,
Okay, so
Francis, right before, like, how did you immediately see that map is thinly null homotopic? Is it by the computation of the rank, or is it something like
this fact here?
simpler? Yes.
That's what I'm going to explain now. It's not obvious. That's not, at
Oh,
least
okay. Right. Thank you.
Okay, so here's the construction of the thin homotopy. So I'm going to do it in 3 steps. So the first step is I just want to think about the real projective plane as a disk with the antipodal boundary points identified. Right, so I've drawn this disk and I have like this top part S and it's glued to this bottom thing that's called S. And I just want to point out that if we take this thing, we can also collapse the entire boundary to a single point, and that will produce a sphere. And that means that we have a map from RP2 to the sphere, right? So now if we compose this map here, the map from S2 to RP2, with the map that collapses the boundary to a point, we get a map from a sphere to a sphere, which what does it do is it takes the equator and it kind of shrinks it to a point and sort of it twists the sphere up onto itself. And now this does have a fold cancellation. Like I can take this blue dot, the blue dot corresponds to the equator, and I can sort of open it up and sort of fold the surface, kind of cancel this fold. Okay, so any map that factors through this map here is going to be thinly null homotopic. So what I'm going to do is I'm going to give a homotopy of the original map to something that factors through this map. If I can thinly homotop my original surface to this one, then I'm done. Okay, so here's how it works. So I'm going to denote my map G from RP2 to Rn. And I'm going to let gamma denote the generator of the fundamental group of RP2. So that's this S here on the top half of the boundary, right? In RP2, this is a loop. And it shows up sort of twice on the boundary. That's what I'm calling gamma. And I'm going, the gamma composed with G, this is a loop in Rn, and it's contractible because Rn is contractible. So I'm going to let H be a null homotopy. And its image is going to be a surface, right? It's going to be like a disk, which kind of bounds that loop. And I've drawn a surface here of the homotopy. So on the top edge, it's my loop gamma, and on the three sides, it's a base point. Okay, so what I'm going to do is I'm going to take my original map G, and I'm going to stick this to the boundary in the following way. So I'm going to take my original, this is my RP2, which is like a disk where I'm identifying the antidal points, and I'm going to stick the homotopy twice on the boundaries. So this gives me a new map, which now sends the boundary to a point. And I claim that my original map G is thinly null homotopic to this new map. Basically by using the homotopy that I stuck on. And that's basically the argument. So I've taken my original surface. I've used this disk that kills the generator pi1, and I've stuck it onto the boundary, and I sort of deformed my map into this new map, which now sends the boundary of the disk to a point. Okay, that's the construction. Any questions about this?
So if you look at the boundary of the inner yellow region in the middle picture,
Yeah,
that's sent to a non-trivial loop in
yeah,
Rn. And as you pass through the red region, that thing's getting contracted.
yeah.
And then what happens in the white region? That's a point.
At the top?
After you pass through the red region, you reach the white region.
Oh, that's just intermediate.
Sorry,
That's sort of intermediate.
which means all of that is sent to a point.
No, only once it gets to the blue part. I just tried to do.
I was trying to do it step by step.
Yeah,
You start at the boundary of the inner yellow region.
yeah,
That is sent to a non-trivial path in Rn.
yeah,
As you move through the red, that thing is getting contracted to a point.
exactly.
And then if you go a little bit further, what happens then?
No, you stop when it gets contracted to a point. That's when you stop.
I'm trying to I'm trying to describe the central picture is supposed to be giving me a map
Yeah,
from this larger disk into Rn.
yeah,
I was trying to tell you a story of what that map is actually,
yeah.
but
Yeah.
you don't want to tell me what happens after I reach the boundary of the red region.
You mean on the inside or on the outside? So in this part here, it's the original map.
Yes.
In this region here, that's the homotopy H. That's
What
this
region
picture
are you
here.
pointing to? I don't-
So this region here,
Is that the red region, the white region, or the blue region?
I mean, all three. I mean, this picture here, red,
So that's one copy of H.
yeah, and then there's
So
another
where's the second copy of H?
here.
Oh, I see, I see. I thought your red and blue were two copies of H.
No,
I couldn't figure out why they were red and blue.
sorry, I used different colors, but it's like I've taken this and I glued it on the top half, and then I also glued it on the bottom
see.
half.
Let's see.
Okay. So this argument can be generalized to a sort of an injectivity theorem for the surface signature. So the theorem, which I'm stating here in a sort of imprecise way, which says that if X is a sufficiently regular surface, for example, piecewise linear, such that the signature is 0, then X is thinly null homotopic. In other words, for sufficiently nice surfaces, the signature is injective. So that generalizes the theorem of Chen. So what I mean by sufficiently regular is I mean that the image of the surface has to be sufficiently nice. For example, it could be a CW complex if the image of my map. So a general image of a smooth surface could be horrible. Because it's horrible, we don't yet know how to deal with it. We have an approach, but we haven't been able to make it completely work yet. But for sufficiently nice surfaces, this will work, and the argument is very simple. So here's the idea. So first of all, it suffices to assume that the signature is closed. That's because given the signature of the surface, you can also extract the signature of its boundary. And you already know that the signature of the boundary path, I mean, that signature is injective. So if that thing is trivial, then the boundary should be trivial. So any surface with trivial signature will be a closed surface. Okay? So we think of it as a map from a sphere into this space Y. Now, we can show then that the image in H2, if you apply H2 to this sphere, it's going to be 0 in the homology of Y. And why is this true? It's because of this other result that I explained, or that I mentioned, this thing here, that the signature of a closed surface just calculates integrals of all two forms. So because of that, you immediately get that this is true. Now, if the fundamental group of Y was 0, we would be done, because by Hurwitz, H2 is equal to pi 2, which would imply that the surface is null homotopic within its image. So it would be null homotopic in a two-dimensional space. Okay, so we're sort of obstructed by pi 1 of Y if it's non-zero, but the solution is easy. You just add disks to kill the fundamental group.
Sorry, what's Y? Is that the image?
It's the image, yeah.
Oh,
Yeah.
sorry, I see.
So in the previous example, X was the map from a sphere and Y was RP2. RP2 has non-trivial fundamental group, so we just killed that by adding in that homotopy. And that's the general, essentially that's the argument. Okay.
So is this using ideas from your example? I couldn't, from the example of S2 to RB2 being the previous one, thinly null homotopic.
Essentially, yeah. I mean, in the example, I told you what the explicit homotopy was, but I could have told you abstractly that it existed. Yes, using this argument. But the idea was, right, that we couldn't do it within the image of RP2. Right, so this map from S2 to RP2, it sort of has degree 0. It's 0 in homology, but it's not 0 in homotopy, right? This map is the generator of pi 2. So H2 and pi 2 are not the same, but that's because we have a pi 1.
Pi 1 of the image.
Pi 1, yeah, of RP2.
Yeah.
Yeah, which is generated by what was it? By this loop here. So we just killed that loop by adding a disk, a new surface that kills this thing. And then by moving through this new disk, we're able to thinly null homotopic to a point.
Isn't it disturbing that you need to look at the fundamental groups of the image of the map in order to make this argument work?
Yes. Yes, it is.
Yeah, could you, for 5 seconds, go back to the sketch of the proof of the... Okay, thank you.
words, I see. So you need you need that the image is sufficiently loose,
Yeah,
not that the domain is sufficiently loose.
exactly.
So when you say let X be a sufficiently regular surface, that's a condition on the image of an.
Exactly.
I see.
Yeah, that's what this.
So it's not enough, for example, if X were smooth.
Exactly. Smooth surfaces can have horrible images.
Oh dear. Okay.
Is this how I should be thinking of this in terms of some like failure of her image?
Yes. Okay.
Yeah, because the surface holonomy, right? One of the things that it should be able to do is it should be able to detect second homotopy, as opposed to just second homology. We don't need fancy invariants to detect second homology. We could do that with closed forms and so on. But for second homotopy,
I,
higher parallel transport should be able to.
no, it doesn't really detect second homotopy. Well, it's more subtle. Well, I mean, it's more in between.
And this the signature itself, should I think that it tells you information that pi2 has that the homology does not in general, or is that too vague? Is that not accurate? The surface signature in general.
So if I have a general surface and I embed it into Rn, and then I take something in pi2 of that surface, and then I take its signature, or I take it up to thin homotopy, it will only see its image in H2. But it sort of sees the image in H2 of like every possible embedded surface.
I see.
Okay, so now I want to switch gears and talk about piecewise linear paths and surfaces. It will still have something to say about thin homotopy near the end of this. So let me just recall again, we have this thin path group, right? Paths up to thin homotopy in translation. We have this homomorphism from tau1 v to v, which is the displacement. And we can obtain the thin fundamental groupoid as an action groupoid. Okay, so within this group, there's an interesting subgroup, which is the group of piecewise linear paths. So they're paths that are just concatenation of line segments. And this piecewise linear path group has an interesting universal property that characterizes it. So first of all, PL0V is equipped with a map. I'm calling it eta V from V to PL0V, which it just sends an element V to the sort of the straight line path. Okay, and notice that this map is not a homomorphism, but it is a homomorphism when you restrict it to one-dimensional subspaces. If I concatenate two collinear paths, it's just the longer path. But if I concatenate two paths that are not pointing in the same direction, I can't just take the displacement path. Okay, so here's the property, is that, so let V be a vector space, let G be a group, and let F be a map, which is not a homomorphism, but it restricts to a homomorphism on each one-dimensional subspace of V, on each line. Then there is a unique group homomorphism from this group of piecewise linear paths to G, such that it makes this diagram commute. Okay, so using this property, you can produce a bunch of maps in a sort of a very simple way. So using the identity map from V to V, so that certainly restricts to a homomorphism on one-dimensional subspaces. So you get an induced homomorphism, and that's just the displacement of the path. the one that I described before. Another example is you have a map from V into tau 1 of V, which sends any vector to the straight line path. And this induces a realization homomorphism. So that's a way of viewing this algebraically constructed group of paths as a subgroup of this group of thin paths. Does that make sense? And third, well, we have the exponential map, which is sort of well known not to be a homomorphism, but it is a homomorphism when you restrict it to one-dimensional subspaces, because the Freely algebra of a one-dimensional space is abelian. So the exponential map is a homomorphism. And so this induces a homomorphism, which is the signature.
You said the free algebra restricted to one-dimensional subspaces is abelian, and that's why this gives a homomorphism.
Exactly, because the exponential map is a homomorphism when you have an abelian Lie algebra. Okay, so this explains from the piecewise linear setting how you can get the signature sort of in a very simple way. It's actually interesting to consider not the groups, but the groupoids. It actually buys you something. So I just want to mention this. It's going to be a sort of a preview of what I'll explain further on. So remember, we have these three homomorphisms. We have the displacement homomorphism. Well, this is the one that I just explained. You have the smooth version that takes the displacement of the path. And you also have this projection map. It's sort of the truncation map that takes a non-commutative power series and just extracts the linear part. So these are three homomorphisms, and they give you actions of these three groups on the vector space V by translation. Right, and they're affine transformations, in fact, because they're translations. So from that, we get these three action groupoids. And in fact, you can let V be any vector space, and in fact, think of it as an affine space. And you get in this way three functors from the category of affine spaces to the category of groupoids. So I claim that these constructions are functorial. If I have an affine transformation between vector spaces, it induces homomorphisms between the groupoids. Okay, now these homomorphisms for all V in affine spaces, well, they give rise to these maps, right? So we have this realization map from PL0V action V to tau 1 of V action V, and then we have the signature map. And when you compose them, you get the piecewise linear signature. And you can think of these as assembling together into natural transformations from these functors. So these are three functors on the category of affine spaces, and there's natural transformations between them. And the sort of, well, why would you phrase it in this abstract way? Well, because of the following theorem, is that the piecewise linear signature is in fact the unique natural transformation from piecewise linear paths to this groupoid of formal paths. The argument is very simple, because when V is one-dimensional, well, then this, the Freely algebra then is abelian, so it's just V, and so its integration is V. So this group here just becomes V. And so this action groupoid is just a pair groupoid. And there's a unique homomorphism from any groupoid to the pair groupoid. And then because piecewise linear paths can be factored into one-dimensional paths.
Why is K0V isomorphic to V?
Because if it's an abelian Lie algebra, then the bracket of any two elements is 0. If it's one-dimensional, then it's abelian, so the bracket is 0. So when you just start taking elements of V and taking their brackets, you don't generate anything new, you just get V.
So the exponentials of all of these elements, they all look like 1 plus some element of V.
Well, they look like no, it's just that every element is an exponential of just something in V, because it's
So the isomorphism is as what, as topological spaces or as abelian group?
just as
It's
abelian
groups.
Yeah, just as abelian groups.
So the exponential is an isomorphism.
Yeah,
That's okay.
exactly. So because of that, I mean, yeah, this groupoid just becomes the pair groupoid, and then any groupoid has a unique map to the pair groupoid. So then this is V being one-dimensional, but piecewise linear paths are just factored as one-dimensional paths. So because of naturality, it forces the definition in general.
So in particular, these functors pi, PL, and pi k have no automorphisms, no non-trivial automorphisms. Because you're saying there's a unique natural transformation.
I guess so. I'm not sure. So you could think of this, if you want, as an alternate definition of the signature. And in fact, because piecewise linear paths are dense and smooth paths using the Lipschitz topology, you also get that the signature of smooth paths is the unique continuous natural transformation. Okay, any questions about up to this point? So I'm going to now move to piecewise linear surfaces. So the part about paths is meant to be a warm-up.
So what is it about PL paths that is providing you with this alternative, much simpler definition of the signature?
It's the universal property that I mentioned.
Which one?
Yeah, so I think in fact you could use this as a new way of, as like a different way of defining parallel transport, because you just have a unique map like this, and then you can extract the parallel transport of any connection algebraically out of the signature of a path.
But wouldn't you agree that it is consistent with the original observation of Chen that you just, what physicists say is that it's the path ordered exponential.
Yes,
That's
exactly.
literally what you're saying.
Yeah,
You have finitely many path segments, each one is an exponential, you take the ordered product.
exactly. It's a realization of that fact.
Yeah, and then you're saying that the limit will take care of the continuous path.
Exactly.
Okay, yeah.
Okay, so now I want to talk about piecewise linear surfaces. So there's an interesting cross-module living inside of this cross-module of smooth surfaces, which is a cross-module of piecewise linear surfaces. Okay. Now I'm going to give a description. So again, it's a completely algebraic construction. There's no geometry, and then you can realize it in terms of geometric surfaces. So I'm going to explain the construction. So this group is just the group that I just talked about, piecewise linear paths. So I need to describe this group here, the group of surfaces.
Just so that I remember correctly, PL0V is piecewise linear paths mod translation.
Yeah.
Okay.
Exactly. Yeah. So now this will be surfaces. And this is a group, and the way that you should think of that is generated by pictures like this, what I'm calling kites. So it's a little surface that lives in a plane, and then it has some sort of tail path attached to it. And this group will be sort of generated. It'll be products of these little elements.
So the polygon is in two-dimensional affine subspace of B.
Yeah,
And then this tail
it
is
can be any,
3D,
yeah,
or it's
any D.
ND.
Yeah, ND.
Yeah.
Okay, so I'm going to give I'm going to first give the construction, and then I'm going to give a universal property characterizing it. Okay, so the first step is I'm going to look at the kernel of this displacement map. And the kernel is a group of piecewise linear loops, closed paths. So that's a subgroup. Now within this, there's a subset, which I'm calling planar loops. So these are loops that are contained within a plane. So this is a condition on a loop. And in fact, any loop that lies in a plane determines a unique plane. Okay. Now I'm going to define what is a kite. So a kite is just a planar loop and a path. Okay, so now I'm going to define a group in this way. So what I'm going to do is I'm going to take the free group generated by these kites. So again, a kite is a picture like this. So I'm going to, right, it's a planar loop along with the tail path. So I'm going to take a free group generated by these kites, and I'm going to pose an equivalence relation that I'll explain in a minute.
So K of V is a subgroup of PL0 cross PL0?
It's not a group. Because planar, if you have two loops that are contained in a plane, if you concatenate them, if you take their product, they're not necessarily contained in a plane anymore.
Right.
So you just take a free group, and then you have to take a quotient. Okay, and that will be my that will be a group of surfaces, and it has a sort of a natural map to PL0 of V, which it takes the path and this loop, and it just takes it to this loop here. Which basically, so here's a picture of a planar loop. So it's a path and then this planar loop. And the boundary of it is like I follow W, then I go around B, and then I come back along W inverse. So that's this map here. And there's also an action of PL0 on this thing, which is just given by taking a path and just concatenating it with this tail path. And my claim is that this thing is a pre-cross module of groups. Okay, so I have to tell you what these equivalence relations are. And I'll do this on the next page. Okay, so these are the generators. And I'm taking a free group generated by these, and here's the relations that I'm going to impose. I'm going to impose two relations. The first one is what I'm calling kite factoring. So here's the idea. So in this picture, I've taken this picture, which is like a geometric kite, and I've broken it into two parts, B and W. B is required to lie within a plane, but W is not allowed. W can move anywhere. But what if, for example, just this green component of W, if that lied inside the same plane as B? Then I can consider that as part of B and consider W just the red, blue, and yellow part. So it's not necessarily clear which part should be the tail path and which part should be part of the loop. So that's what this equivalence relation is saying. It's just saying that you can exchange paths between the loop and the tail path as long as you maintain this planarity. Okay, and then the second one, I'm calling it cancellation of folds. It's sort of the key relation. So I've written it out here, but let me give a picture. So I have these two kites, and I'm just multiplying them together freely in the group. But what if the combination of B1 followed by this purple part And then B2, if that part remains in a plane, if that part is planar, then I should consider this as a kite, where this kind of B1, U, B2, U inverse is itself my loop, my planar loop.
What happened to W1 and 2?
Well, yeah, so W1 is this green part. W2 is the green part plus the blue part. U is W1 inverse W2, which just gives you the blue part. So if B1, U, B2, U inverse is planar, then you should impose this relation.
So did the first segment of W2, did it coincide with W1? Or
Exactly. Yeah, the first segment of W, so it gets canceled out.
I see.
Yeah, so yeah, so W1 B1 times W2 B2 is equal to this, where U is W1 inverse W2 if this loop is planar. So notice that this imposes cancellation of folds. Okay, so this gives you a pre-cross module of groups, and to get a cross module, you just impose the Pfeiffer identity. You just impose it.
That's another part of the quotient.
Yeah, you have to impose an extra relation, which is the Pfeiffer identity, and that gives you the cross module of piecewise linear surfaces. So here's a result, which is that there's actually a unique realization map from this algebraic construction to the smooth cross module of smooth surfaces, which is natural in V and extends the path realization map. And this homomorphism is injective. So it really realizes this algebraic construction as a sub cross module of surfaces of this surface cross module. The interpretation of this is that the non-local nature of thin homotopy is a sort of a formal consequence of fold cancellation and the Pfeiffer identity. In other words, the interchange law. So if you only require cancellation of folds and you require the Pfeiffer identity or interchange law, you automatically get all of these non-local cancellations.
But wouldn't you go further and say that the Pfeiffer identity is where the non-local stuff is?
Yeah, exactly. Yeah.
Not a fold cancellation. Fold cancellation is like normal fold cancellation.
Well, yeah, but Pfeiffer allows you to sort of move things around and then apply fold cancellations.
See.
So from this perspective, thin homotopy is the sort of the minimal equivalence that you can really put on. Right, if you want fold cancellation and you want a two groupoid or a two group, you need to have these non-local cancellations.
Sorry, could you say again why you were calling this non-local?
Well, this example here of the example of RP2, the one that I talked about in the last section. This one is non-local because there's no folds that are being canceled. Like the parts that are canceling each other are not connected in the domain.
I see.
Okay, so now I want to explain the universal property of this PLV. So there's now two canonical functions into this. So you have a map from V to PL0V, which is the one that I described before. You take a vector and you just send it to a line segment. And then you have this map A to 1 from V cross V into this group of surfaces. And what you do is you just take the, given two vectors, you take this triangular surface spanned by V and U. So in other words, the boundary is V, U minus V, and then minus U.
This is the kite now we're talking about.
Well, just not the tail part of the kite, but just the disc part of the kite. So this is a special kite where there's no tail path.
Okay, but that is a full element in PL1,
Yeah,
which is a kite with no tail.
yeah, exactly. It's a very, yeah, it's the most basic type of surface. It's a triangle. Okay, so here's the universal property. So V is a vector space, and H is just a cross module. And then you fix two functions that are like eta 0 and eta 1. So F0 is a map from V to G, a set map. And F1 is a map from V cross V to H. So you should think that it takes a line segment to some sort of path in G, and it takes a triangle to a sort of a surface in H. Okay, and these are the properties. So F0 needs to satisfy the same property as before, that it restricts to a homomorphism on every one-dimensional subspace. The second property is that V cross V, the map F1, it should be trivial on all linearly independent pairs. Well, why is that? Well, I mean, if V and U are linearly independent, then this surface is very thin. It just lives on a line. And therefore, it's thin homotopic, thinly null homotopic. So it should be trivial. That's the claim. Then the next condition, it's sort of what I'm calling a triangle identity. It's just saying that if you take the F1 of VU, so you get this triangle, and you take its boundary, it should be the corresponding boundary element that you get from F0. So if I go back to the picture, it's saying I take I take this surface of VU, and I take its boundary, that's V, U minus V minus U. That's exactly what this is saying. Okay, and then there's one more property, which is called the tetrahedron identity. Here's a picture of what's going on. So I have three vectors, now W, V, and U, and they sort of span a tetrahedron. So I have four sides of the tetrahedron. I have this side here that's basically made out of V and W plus V, this side here. I have this side here, which is made out of, well, V plus W and U plus W. And then I have this back face, which is made by W and U plus W. So those are the three sides. And then you have the top face. And it's a little bit different because the top face, well, if I take V and U and it will give the same triangle, but sort of down here. So you have to attach onto it a sort of a tail path. That's this W. This W is a tail path, and that's this thing. So what this equation here says, so these are the three sides of the tetrahedron, and this is the top side. And what does it mean for these to be equal? Well, that would be saying that that these three sides are equivalent to this top face. So they're definitely homotopic, but they're not going to be thin homotopic if this tetrahedron has a volume. If this tetrahedron has a volume, the homotopy from the top face to the three side faces sweeps out the volume of the tetrahedron. So the condition is that this equation should be true whenever these three vectors lie in a common two-dimensional subspace. In that case, the tetrahedron is flat. It's contained in a two-dimensional subspace, and the homotopy is therefore thin. So under these conditions, you get a unique morphism of cross modules. Okay, so let me just summarize now. So we have now these three cross modules, this PL1, this cross module of smooth surfaces, and then this formal cross module, this sort of cross module of formal surfaces. And these are all functors from the category of vector spaces to the category of cross modules. And then we have all of these maps, which are natural transformations. So the signature of a smooth surface is a natural transformation from tau to k, from the smooth surfaces to the formal surfaces. We have this realization map, R, from PL to tau. These are both natural transformations. And we can compose them, and we get a sort of a piecewise linear signature, which is a map from PL to K. Okay, and then the theorem, which is similar to what I explained before, is that the piecewise linear surface signature is the unique natural transformation that extends the piecewise linear path signature. And then as a result, the smooth surface signature is the unique continuous natural transformation that extends the smooth path signature. Okay, and then essentially one more theorem, which, well, there will be two more things. So this one is, how do you explicitly compute the signature? So here's a formula for how you actually compute the signature. So I guess this answers the question of Gabriella. So this group of formal surfaces, it canonically embeds into this product, where this TV is the algebra formal non-commutative power series. And this thing is this vector space of formal two currents, just power series, tensor wedge 2 of V. So there's a canonical embedding like this. And when you use that embedding, the surface signature canonically decomposes into two components. So it sends a surface to a formal current and a non-commutative power series. And here are what the components. So given a surface, the part that lives in the non-commutative power series is just given by taking the path signature of the boundary. The part that lives in the currents, well, it's computed as follows. So associated to X, there's a canonical closed surface that you can define, which I'm calling the cone of X, and it's defined like this. So X is my surface, and there's maybe a tail path attached. And you just take, for every point on the boundary, the straight line connecting it to the origin. So you sort of take a cone, and that's a closed surface. And so what you should do is you just take the integral of all polynomial 2 forms over this closed surface, and you just record them by including the coefficient, the corresponding current. Okay, and then the last result, well, is what I mentioned before, is that the piecewise linear signature is injective. Okay, so I'll end there.